Hi, Professor. Thank you so much for joining us today. It's a pleasure to speak with you. So I want to start off that you wrote a key paper on tensor algorithms. Could you talk a little bit about kind of what tensors are for our audience, how your work has really helped allow deep learning to kind of take off and allowed for large-scale AI applications?
Absolutely. Thanks, Katie. And it's a pleasure to be here, even if that is virtual. And MIT is close to my heart. I spent several years there, and I really cherish the mentorship I got there and the friends I made there. Always great memories from there. Yeah, and the tensor paper, in fact, had its birth in Cambridge, at Microsoft Research New England. I was visiting them, and my interests are in learning latent variable models. How you can extract hidden variables in an unsupervised way, right? So, and this is key to solving hard problems in machine learning, because most of the time we can't label everything we want to discover. There are many aspects we may not even know what to label or how to label. For instance, discovering new materials or new drug molecules, especially now with COVID around, right? Those cannot be framed as supervised problems, but unsupervised learning problems. So that was my interest, and I was exploring efficient algorithms to solve it in large-scale data, right? So one anchoring example is extracting topics from documents. And if you now have billions of documents and you want to automatically extract what the topics are, and you can't possibly label all possible topics, right? And also in each document, there may be multiple topics. So how do you enable all this? You can't label them. So you have to learn it in an unsupervised way. And the question we were asking was, how to, first of all, model this kind of relationships between topics and the words they generate, and then how to learn them in an efficient way. And as in life, even in machine learning, a lot of it is about relationships, right? It's relationships among the variables. And in this case, it's a simple intuition that worked, which is to say that it's really the co-occurrences of words that tell me about what the underlying topic is. And if there are co-occurrence of multiple words, then you have more information about the topic. For instance, if I tell you that in a document, the word apple appears a lot, you're not sure, is it a fruit? Is it a company? Right? If I tell you only that, that's not enough information, right? But if I tell you the words apple and orange occur, you're more sure maybe it's fruit, but orange is also a company. So, you can then say, okay, now what if I tell you that the words apple, orange, and banana occur a lot together? Then, it's most likely about fruits, right? So this simple example shows that you have more information about co-occurrences of many words together. You can be more confident about discovering good topics. And in fact, this is very simple, right? We are ignoring all the language structures. We are ignoring the order of the words. We are merely counting how words occur together. So simple, that's why you can do it at scale, but it's also capturing the relevant information for topics. And it was this intuition that led us to ask, if you're modeling pairwise co-occurrences, just two words occurring together like apple and orange, I can count for every pair of words across all documents. That's just my correlation matrix, right? So I can represent that as a matrix. And then we hit a wall when we realized, oh, maybe this is not enough information. What if I need now more words to incorporate? I incorporate co-occurrences among triplets of words. And then we realized, oh, this is when we require tensors. Before that, I had no background in tensors other than my course in quantum mechanics, which was a great course. But, I was never kind of thinking that would come in handy. So this realization that tensors can be a great object to model these higher order correlations in data was the starting point, right? And then the question was how to extract that information from data in an efficient way. with matrices, the most common algorithm is factorization, right? Finding a low rank decomposition. For cleaning up data, you can do PCA or principal component analysis with it. And similarly with tensors, the question is, what are some basic operations and ways to extract useful information? So the similar intuition holds that you can look at low rank factorizations and extract the most relevant components. And this, in fact, we can prove that it extracts the relevant topics. So if you make some simple assumptions on how the data is generated and the topics are not being redundant, right, then you can prove that it's extractable using tensor methods, which was very surprising because until then, there was no guaranteed methods for these classes of latent variable models to be able to learn efficiently. Right, and so the theory was great to say, like, tensors now give you more information matrices. If you now do tensor factorization, you can recover components that you couldn't if you just had a matrix. And that's intuitive because now we are looking at higher order correlations, but also there is now efficient algorithms that can extract information from them. And that was this key finding that we can do this at scale. We can, in fact, parallelize them with very similar operations as matrix operations. And in fact, even get higher efficiency due to that parallelism that made it compelling, that it was a great piece of theory, but also practical to scale up. And when I went to Amazon Web Services, I deployed this on the cloud infrastructure, on SageMaker, on the Comprehend tool, and that's what's running today for topic modeling there. And it can process billions of documents and give you topics very quickly. So seeing that from a theoretical concept all the way to a working tool has been very fulfilling.
You're also doing incredible work on AI for science, and kind of bringing AI to the lab bench and to other areas to help make sense of the large data sets coming out of kind of applied areas. Can you talk a little bit about your work there, what you think is needed in AI to allow it to interact more with biology and the climate discipline and different areas?
Yeah, I'm very excited about the AI for Science initiative that I co-founded with Isong Yu here at Caltech. Caltech has a very, it has amazing set of researchers in all of sciences, right? And including Nobel Prize winners. And every day I'm amazed and inspired by the great work that happens here. And naturally, there is a role for AI in so many of these scientific areas. And we wanted an initiative that can bring all the people together, the AI researchers and the domain experts, and aim to solve really ambitious problems. For instance, I'm working with a seismologist in understanding right, how the earthquakes propagate, and there is no ground truth here, right, because this happens down in the earth, and how to apply unsupervised learning there. Or in chemistry, like how we can speed up computation of quantum energy calculations for molecules of large sizes, like drug and ultimately protein molecules. And the current tools are very heavy and traditional without any learning. And now the question is, what's the right form of machine learning to do there, but not lose that domain expertise and the domain knowledge, right? Because if you naively apply a neural network to these problems, you can only interpolate, meaning you can only have that work on data that is similar to the training data, which is not very useful. I can have training data, I can do these expensive computations, say on molecules with 10 or so atoms. But what I'm really interested in is molecules of maybe size 80 or 100 atoms, right? And just plain deep learning methods are not able to do that. And that's why to extract the right invariances from the domain knowledge, like we, for instance, extracted molecular orbital features. And these are very cheap and quick to extract from traditional tools, right? And then on top of it, apply deep learning of the right kind using graph structured networks that can incorporate, again, the structure of the molecule. And building in that right domain knowledge and structure with the flexibility of tools like deep learning is the balance, right? And that's how we can make progress. And that's the aim of AI for Science, not to kind of directly apply a known tool and say, here we made the progress. Sure, that's the first step. But most of the time that doesn't lead to progress because these are really difficult problems. We are trying to do zero-shot generalization. We are trying to maybe discover new materials or, do early prediction in earthquakes. All these are extremely important problems as well. So we have to be careful in how we apply machine learning. Most of the time, it's not a quick solution, a black box, say this is it and it's done, right? It requires close collaboration with the domain experts, for AI researchers like me to also understand, right, to an enough extent, what is the underlying math here? What is the structure? What is known, what is cheap to compute, what is expensive to compute, and then work with the domain experts together to bring in the right machine learning ideas. And so very excited about these prospects. Another exciting thread in my group has been in neuroscience, working with Doris Sau at Caltech here on how the brain mechanism can inspire us to create better artificial neural networks, but also the other way, right? How we can use the current neural network tools to understand the brain better and its mechanisms better. And so that's been exciting as well.
I also find that very exciting. Do you think, you kind of mentioned it, but what do you see as some of the biggest outstanding challenges within machine learning? Is it on the algorithmic side, the hardware side, the data set side, kind of a mix of them in between?
Yeah, it's really a mix, right? Like you mentioned, data, algorithms, and hardware. To me, that's the trinity. And what made this deep learning revolution possible is that synergy of the trinity, right? Because the internet was kind of growing on its own. The neural networks have been there since the 30s, but kind of they didn't work in the past because there wasn't enough data. The hardware, the GPUs were evolving to give us very efficient parallelized operations, right? But they weren't put together. And once, right, the early researchers realized that, oh, we can kind of bring all these together. We can create the ImageNet data set. We can use neural networks on them and we can run them on GPUs, right? That created this deep learning revolution. And to me, I think for the next decade, all of these should evolve further, right? Our ability to collect better data, especially multimodal data. And, right now we think of like annotations as just very simple, right? Humans labeling something, but more human in the loop learning and much richer feedback from humans. I think that aspect of data will evolve over the decade. And in terms of algorithms, we need better algorithms to deal with limited supervision or unsupervised learning, being able to incorporate these kind of domain knowledge and structure, being able to easily adapt and even learn online, right? Like the way we do. And finally, I think the most important aspect is to be robust. The current networks are brittle. I mean, you can't put them in any sensitive applications. There's safety criticality that's needed, right? You can just perturb the data a little bit and these networks are completely wrong. So all these aspects have to be resolved in order for us to trust and put these algorithms in sensitive applications. And finally, on the hardware side as well, we need bigger scale, right? I mean, the models are getting bigger. I mean, I don't think we should just do brute force big models, but even with the right algorithm, sometimes you need the scale. I mean, many times, right? You need the scale as well. So we need better, efficient hardware in terms of, right, how to kind of have the data access be controlled, right? Because if you can now bring the compute to the data rather than data to the compute, right, the more and more it's kind of getting there because the data is big and the compute is usually, the primitives are simple enough. And so we'll see more of that convergence happening.
You've also done incredibly important work seeking to democratize AI and address kind of the societal implications of AI. Could you talk a little bit about your thinking in your work there of, are there any core misconceptions you think within the field of machine learning right now, or what can be done to make sure that work in machine learning is really integrated with society and the downstream impacts?
Yeah, I think that's such an important question, but also a hard one, right? Because we now have the wheels in motion, to say, in the sense that we are collecting data from the internet that's heavily biased and imbalanced. There's more data being generated in the Western world, and there's obviously, more, like people in the upper class who are generating data on the internet, right? And an extreme version of this is for training language models. OpenAI used links from Reddit. And for one, I don't go on Reddit. I don't know if you do. Most women I know don't go there, right? Because it's such a toxic place. And so you can imagine, even if they filtered out the most terrible of the words, right, there'd be so many other biases inbuilt in that model. And we see that, and there are researchers who've shown that you can easily get these models to generate highly racist and sexist and homophobic material. And the worrisome thing is, what if now it's in the hands of, right, some companies or even other bad actors, and it's probably already happening. For instance, I think last week there was an API called Genderify that was released. Like, you could type in, I don't know if you saw that, any word there, and it could give like the what the gender is. And first of all, binary genders, that's already a huge problem. And second of all, you could type in any word. For instance, the word professor was only 1.9% female. I mean, this is automating discrimination now at scale, right? And that's what scares me, that, because it was out in the public, there was a lot of people pushing against it, including me, and they finally, right, removed it. But we don't know what happens, right, inside the companies. We don't know what happens inside government agencies and all over the world. And that's a problem, that we need more transparency, we need accountability. The GDPR is a good first step, but it's only in the EU. I think we need more regulation and more understanding of how data is collected, how it's going to be used. And, there's a lot of focus on that aspect, but there isn't much focus on what data goes into training these models and how these models will be used, right? In some sensitive applications like, loan, granting someone loan, or crime recidivism, there's much more regulation, and at least there's some thinking there. But we would now need that to be much broader, right, into all sorts of applications, and that's going to take some time.
Could you also talk a little bit about your trajectory? How did you get into machine learning? Your evolution in the field?
Yeah, I always loved math and science as a kid. And thankfully, I grew up in a family that encouraged that. My mom is also an engineer, and my grandfather was a math teacher. So, I was really lucky to have that be nurtured and encouraged. And when I came to high school, I discovered probability, and that was great to, kind of see it's not just deterministic math, right? You can reason about randomness in the world and talk about uncertainty. And, that was my favorite topic. And when I came to undergraduate studies, I went to IIT Madras, I did electrical engineering. For me, I didn't think much at that time, I guess, about AI, but indirectly, I was doing all the signal processing. I was looking at statistical signal processing. So, those were my favorite topics. So in that sense, that kind of led me to the trajectory of first working in signal processing and realizing, oh, this is, in the neighborhood of machine learning, and machine learning, has a lot of challenging problems and interesting data. And so kind of I found my way into that.
And you're also the professor at Caltech and the director of machine learning research at NVIDIA. How have you titrated between academia and industry?
Yeah, I think these is a really an exciting time, right, in terms of partnerships between industry and academia. I think for academia to stay relevant, they really, want to have that connection with industry, and also for industry, at this day and age for AI, there's so much to be developed, right? There's fundamentals to be still further developed. It's not just like push of a button and this technology is ready. And so I think it's in interest for both of them to have this close connection. And to me, I think it's great. For instance, I can work on the foundations at Caltech. I can work on AI for science. On the NVIDIA side, there is amazing engineering that is happening, and experts in computer vision, language, speech, all these domains that are, challenging, as well as robotics, autonomous driving, right? So there is great test beds for that and data for that. So how we can kind of bring the two together, right? That's my goal.
And do you have any advice for students interested in machine learning or getting into the field, high school students, undergrads, or early grad students?
Yeah, for high school students, there is an amazing program you may be aware of that's called AI for All. That's a nonprofit, that gets women and underrepresented minorities in high school to work with top professors across the country in AI for the summer. So that can be a great starting point to discover AI and kind of do hands-on AI research and apply them to various interesting domains. And then, undergraduate, many schools, including Caltech, have a major in data science, right? And that's, I think, a great mix, because it's some of the CS courses, EE courses, statistics courses, the right relevant mix that is needed for machine learning, because it's such an interdisciplinary field. The traditional majors don't give all the grounding. So I think that those kind of courses would be great. And then also, like organizations like fast.ai have all the notebooks and the code available online. There's now so much material, right? So kind of being able to do a lot of hands-on trials as well, using all the online education tools, and including NVIDIA has Deep Learning Institute that's also application specific. For instance, you can get an idea of all the blocks that go into building an autonomous driving tool, right? So all the way from how to prepare the data to what kind of models, and how to visualize the results. So there's so much of resources available now for more hands-on trials. So it's a mix of both foundations and the ability to use the tools. I think will be a great path for success.
Thank you so much. That's all fascinating. It was great speaking with you. Really appreciate you taking the time. So thank you so much.
My pleasure. Thank you.